Thank you for joining us for this very special episode of the Stem Cell Podcast, live from ISSCR 2025. I'm Dr. Daylon James with Dr. Arun Sharma. We're the co-hosts, and this is the Stem Cell Podcast, where we culture knowledge in stem cell research by talking to some of the brightest minds in the field. And looking out here today, and since I've arrived, I can say definitively there's no greater concentration of those bright stem cell scientist minds than here at the ISSCR every year. But this year in particular, and we're delighted and privileged to share this conversation with all of you. And bright is the word. We're here in the City of Lights, and the tagline of this year's meeting is illuminating the future, which I think is really apt because we're talking to a couple of the architects of not just the tremendous progress that we've made over the last 20 years plus, but also those who are kind of sketching out the roadmap for the future of stem cell science. So illuminating the future is a really apt title. And that's what we're here to highlight today, the amazing work done by this group. But before we get there, I have a couple specific acknowledgments I'd like to make. First, to the Stem Cell Podcast team and STEMCELL Technologies, which is a big biotech that does all the little things to foster communication and collaboration in science. Also, want to acknowledge the ISSCR, whose administrative staff and leadership has not only scaffolded these meetings, not just here, the annual meeting, but over the course of the year, all over the world, to bring all of us scientists together, but also shown amazing leadership and guidance, and again, the metaphor of the light, providing a beacon and a guiding light for all of us stem cell scientists and the greater community to adhere to some guidelines and a framework for moving forward. So with that, I'll hand it over to Arun, who's going to introduce our guest.
Absolutely. Thanks, Daylon. And today we have two guests who happen to be major drivers of that rapidly advancing landscape of stem cell biology, and who are also really representative of the amazing science that's happening here in China that is, quote, illuminating the future, like Daylon alluded to. Joining us today, we have Dr. Hongkui Deng, who is the Shangjiang Professor, Boya Chair Professor, and Director of the Institute for Stem Cell Research at Peking University. He's also the co-founder and chief scientific advisor at Reprogenix Bioscience. His work really has been incredibly foundational in the field, laying the foundation for chemically induced pluripotent stem cells and their application and clinical therapies. So everyone, please welcome Dr. Deng. And we also have Dr. Candice Liew, who trained in the Deng Lab, establishing many of the protocols and principles underlying the human trial of iPS-derived beta cells, and who is currently leading the R&D team at Reprogenix Biosciences that is scaling up the manufacture and the application of these cells. So let's give a big round of applause for Dr. Liew. All right, thank you so much for both of you for being here. This is going to be really exciting. We're very excited to talk a little bit about the technology and the applications. So let's start things off, big picture. It's, of course, an incredible time for iPS technology. We've discussed this at the meeting and on our podcast a lot. iPSCs are being used to generate numerous cell types that are being talked about here at the meeting for clinical, for translational applications, for basic science as well, disease modeling. Traditionally, as we all know, iPSCs have been generated via the genetic overexpression of these critical pluripotency factors, such as OCT4, such as SOX2, and hard to believe they were described about 20 years ago, right, by Dr. Yamanaka, Dr. Shinya Yamanaka. And in contrast, chemical reprogramming achieves the same goal of iPS production in a different way, right? Dr. Deng, perhaps you could elaborate a little bit on this chemical reprogramming approach used to generate these chemically induced pluripotent stem cells, or CiPSCs, from somatic cells. So tell us more about this unique cell type and how the idea came about in the first place.
So the chemical reprogramming, actually, I'm interested for chemical biology about 30 years ago. So when I did finished my PhD at UCLA, that's 1995. So at that time, it just come the new concept called chemical biology. So my first priority at that time for my postdoc training is go get into the chemical biology field. At that time in the world, only 2 labs. So many people try to apply for postdoc position for that, but I'm on the waiting list. So and then I continued my postdoc for immunology field. So after my postdoc training, so I have a long-term interest for this chemical biology. So we interested in use chemical, particularly the small molecular combinations, as to change the cell regulatory network. That's the thinking we are doing. And then in 2006, Yamanaka has this really the big breakthrough with the genetic approach. So at that time, I was thinking, what is the future? What is the future technology? So if you look at the Yamanaka, the technology is by genetic approach. So we think the chemical approach maybe is the future. The reason is the several things behind this. The somatic cell all generated from pluripotent stem cell, but the development process is very sophisticated. It's very complicated, generating all different functional cell lineage. The whole process is highly regulated, stepwise. But Yamanaka's strategy is very simple, just one step, just put the thing all the way back. But if you look at that process, maybe the ideal way is also just like a developmental process. So it's a reverse them, but mimicry developmental process. So probably that's the future technology. And secondly, if you look at all these lower animal model species, or you call highly regenerative the animal species, the highly regenerative in the injury conditions can regenerating many tissues, organs. So what we can learn from that? Just like right now, the gene therapy, like CRISPR technology, is learned from bacteria. So what we can learn from the nature? If you look at all the the highly regenerative animal model species, it's not using Yamanaka factor. So they are using so-called responsive to extrinsic stimuli, and to make a de-differentiation, return back, become a fetal-like the cell and generating. So that's the principle behind this. So we try to mimicry that process. So that's the way of what we start in mind for this technology.
Yeah, well, I think we have to be clear about what an amazing achievement it was, because, I mean, first of all, the Yamanaka factors won the Nobel Prize, justifiably. And there were many, I think, tweaks after that to try and optimize, Sendai, less of a footprint, more efficiency, more robust, whatever. But those were all kind of taking the same playbook, so to speak, the same factors, them, and delivering them in different ways, right?
Yeah.
But the chemical reprogramming, you can't, you're kind of in space, right? You kind of have to figure out how to create a chemical or signaling surrogate for each one of those factors, right? So it really was a slog, and you had to invent it. You and your group had to invent it kind of out of nowhere. Can you talk a little bit about, that process, not the detail, but maybe some of the greatest challenges that you face there, and more, generally speaking, is there a major advantage besides the non-footprint, non-genetic integration? Are there advantages or disadvantages to the chemical reprogramming relative to, the classic Sendai nowadays?
The major for technology, the advantage for chemical reprogramming is you really can fine tuning the process, and it's bypass the traditional genetic approach. You just simply use culture media, like the stem cell technology. We use a lot of the medium, but the medium is very, very. If you try to make it yourself, it's very complicated, right? Because is really precisely make a fine-tuning the process, make the
Right, because if this happened in our body, we'd all have teratomas, right? So
Yeah.
you really have to kind of jailbreak the system with the small molecules in order to push them to that pluripotent fate. That's right.
Yeah. So at the beginning, at that time, many labs actually try to interested use the chemical biology as tool to replace this genetic approach. But at that time, I have two different strategies. Many people thinking maybe just use chemicals activating endogenous Yamanaka factor. So try to mimicry that. But my laboratory will think about the strategy is not try to find a small molecule activating Yamanaka factor. We just functional replace them. So we, at the beginning, we just use 3 Yamanaka factor, not use 4 or 2 or 1. So if you use 1 Yamanaka factor or 2 Yamanaka factor, you cannot make a complete reprogramming. And then you do functional screen, say if some small molecule can replace some Yamanaka factor. So first time we find just need octa-4, and we need 4 chemical compounds with the chemical cocktails. Just need 1 Yamanaka factor, and then we can do the chemical reprogram. Can do the reprogramming. So then next stage is important because we find that all these chemicals is not activating the other chemical cocktail is not activating Yamanaka factor. So we then did a one-step screen, try to find the chemicals. We find a very potent nature compound, phosphocline, can replace Yamanaka factor octa-4. But then this chemical cocktail at that time is 5 small molecule cocktail activating, initiate the cell dedifferentiation. But it's not activating the pluripotency network. So actually, the activate the link28 cell 4. If you look at the published work in this highly regenerative animal model species in the injury condition, the activate the transcription factor or called pioneer factor is cell 4, link28. So we find, okay, this is a new pathway. It's completely different than Yamanaka. It's activating not the Yamanaka factor, it's activating cell 4, link28. It's actually this mimicry nature dedifferentiation process. So we get very excited for this. So after this step, then we find to have additional epigenetic barrier. You just do some chemical screen, overcoming this epigenetic barrier, then we get a complete chemical report. So that's the story behind it.
Yeah, it's an incredible technology and, like what you're alluding to, a unique approach in comparison to the traditional Yamanaka approach. And, making iPSCs is an incredible achievement, of course. It's been, like I said, about 20 years since iPSCs were first described. But I think the real power is the application of iPSCs for making various cell types, and one major application for pluripotent stem cells ever since the beginning, even before iPSCs, was applying them for, say, making tissues for the treatment of diabetes, right? For decades, many scientists around the world have been working on this exact problem, generating stem cell-derived islet cells, pancreatic beta cells, of course, that can make, insulin from pluripotent stem cells, embryonic stem cells, iPSCs. The hope is, of course, you want to be able to treat the millions and millions of people around the world who are afflicted with type 1 diabetes. That's part of the hope here. And Dr. Liew, this is exactly what you've been focusing on during your training with Dr. Deng, as well as at your time with Reprogenix. So could you describe the process to actually make these differentiated CiPSCs into functional islet-like cells, and some of the challenges associated with the process, and what makes them suitable for transplantation? So talk about the cells that you actually make from the CiPSCs.
Yes, thank you for the question, and thank you for having us. Yes, so I think today, I was listening to Dr. Takahashi during her plenary session, and she said something that I really agree with, which is that they had with iPS-derived RPE, they first had a cell product, but the cell product isn't the treatment. So actually what we've been doing over the past, decade and a half, really, is first trying to actually get functional islets that have actually therapeutic capacity that is comparable to native islets. So that was the first part. But once we had done that, we realized actually there's quite a bit left to do in order to actually make something that can actually treat people. So that's really the overarching journey. So first, what we do, which I think is what most in the field do, is not very different from what everyone else does, which is that we use CiPSCs. It's the same starting point, which is pluripotent stem cells, and then we do directed differentiation. So what that means is that because pluripotent stem cells have the ability to generate any tissue type in the body, but you want to tell them to become islets. So we do it the best way we know how, which is to mimic the embryonic, the developmental process of islets in the body, and we coax it stage-wise into endoderm, into pancreatic progenitors, and then onto endocrine progenitors until eventually we get pancreatic islets in the dish. So early on, I guess we were trying to figure out, I think there were already protocols, especially including our own over the years. We had also put out some protocols, and people had put out protocols, very notably in 2014. There was a very big breakthrough in protocols. But what we had done is we kept fine-tuning, and I think a lot of fine-tuning was done at around stage 4, stage 5, which is pancreatic progenitors onto endocrine progenitors. Because what happens at that stage is that first you have maybe cells in the dish that are quite homogeneous. They're all pancreatic progenitors. They're all bound to become pancreatic cells. However, they then face a very critical cell fate choice in terms of pancreatic endocrine cells, which they can take many different paths. So I think we did a lot of work in trying to make sure we get a really robust protocol that very efficiently and stably produces enough beta cells, because that's the primary cell type that we're trying to replace. So I think what we were able to do was make sure that our protocol robustly did that. And then thereafter, we found that actually a lot of the functional capacity came along with that, because you had a sufficiently robust protocol. So and then what we found was that in animal models, we started to see therapeutic efficacy. And so that was very exciting. And then we started to wonder, let's start to think about, okay, let's see if we can actually treat diabetes with this. So we did something ambitious, which is we did non-human primate studies. So we went and got monkeys and made them diabetic and then transplanted them, because we wanted to evaluate at a clinical scale. Like if I really were to mimic pancreatic islet transplantation, which is an established procedure in the field, into the hepatic portal vein, we wanted to see if it really could match islets in restoring glycemia in diabetic primates. And so that's what we did at first. So that was when we found out that, oh yeah, they do ameliorate diabetes in these monkeys, then we felt like we had a chance. But we also did find that there was still quite a bit of a gap between what we were seeing in the monkeys and what we were hoping to achieve therapeutically. So we started to develop our therapy by now we have a platform, we have the islets, we have the stem cell derived islets, and now we're starting to change the method of islet transplantation, working back, sort of trying to improve islet transplantation itself using the cells that we do have. And we then developed, using another preclinical study, we then developed improved transplantation strategy. And I think that really cracked it for our subsequent clinical study. So I think I don't know if that answers your question.
It does. Okay. Yeah.
No, it's a great setup. And I love that you led with talking about Takahashi's study, because I was talking to Stefan Irian also today, and Arun and I were talking about Jun Takahashi's study with Parkinson's and dopaminergic cell transplant. And what's emerged in all these is that the delivery, right, the method of getting these cells in there is really critical. And I also love that you described all those incremental pieces, because you guys have to understand that this seminal study in Cell that we're about to talk about in humans having actual clinical results is, the culmination of so many years of work and so many incremental changes where I don't know where you come up with the idea of transplanting into the abdominal anterior rectus sheath. But we got to talk about that for a second. Dr. Deng, so as I'm saying, there's all these steps, right? You get the cells, they work, you show in the mice, go into the non-human primates, then you have to optimize the surgical transplantation procedure. Why do you start with the anterior rectus sheath? And how do you think and why do you think that was such a critical step in leading to increased efficacy?
So actually, we published the first paper, stem cell derived islet beta cell, 2005, 20 years ago. So we published one paper 2009. At that time, we used a human ES cell, iPS derived islet. We can cure mouse diabetes. So quite a long time. Yeah. So
we've been curing mice for decades together.
And then we, because of we put the cell in the kidney capsule. So it's encapsulated in the kidney, right? So then when we moved to monkey trial, so we use a liver protein. At that time, I saw that we work on chemical reprogramming, generating pluripotent stem cell, working on the 20 years for beta cells. I think we can use the traditional strategy for transplantation, like liver protein already being used for 20 years in the field. And then what we find is the one problem for the liver protein. So you put their cell there, actually you lose cell in 1 week, 40 to 80%. So cell not survival well there. And then the major problem is if you use human native the islet, is fine. You put it there, right? You don't need to monitor them. But if you use the iPS derived, put it there. If something goes wrong, you cannot detect them. It's hard to detect there. Secondly, it's hard to retrieve them back. And thirdly, in the monkey, we don't get a functional cure effect. Just get we can improve the situation, but never get a functional cure in the monkey. So then we realized that the one thing is we need to find a better site. And then we say that how we easily get a success in mouse model is because in the kidney encapsulation. But we cannot do that in human that way. So we need to find some new site, just like kidney capsule. So it's an in vivo encapsulation site. You can cell survive there and also encapsulate there. That's the key. Then we say, where is this site? Look at all the literature. The people put it in the skin, muscle, many other places. We put the skin, muscle, like a published study. Cell not survive there well. I would talk to doctors in the surgery. This is that's the new site to suggest this potentially so we try in the monkey. So we try the liver protein one and also this new transplantation site. Only in this new site we get a functional cure in the monkey. Wow, we'll say that site is more like a kidney capsule. So the cell easily get vascularized, and the survival much better than other place. So that's how the story comes.
Wow.
Yeah, I didn't even consider that. Yeah, but it makes perfect sense now. It's building on that idea of using the kidney capsule from many decades ago, and here you are. I think that's an ingenious approach. Really, really exciting. One of the big hopes of iPS technology is the patient-specific nature of the technology, right? I mean, because you're making these cells from a patient's own genetic material, the thought is that there's more immune tolerance, right? And Dr. Liew, perhaps you could talk a little bit about this as well, about the immune tolerance side of the study. I mean, this particular individual that you highlighted in the study had a history of liver transplantation and existing immunosuppressive therapy. So how was the immunosuppressive regimen managed post-transplantation to prevent rejection while also minimizing the risk? I mean, we are using iPS-derived cells, but it's still something that you have to consider, the immune tolerance side of things. So talk about that.
Yeah, so I think with our first in-human trial, our purpose really was to determine the safety and efficacy of the CiPSC islets themselves. We want to know whether or not they can actually, how safe it can be, and also therapeutically how effective it can be. So that was the focus of our study. So our rationale at the time was to sort of transplant into a patient with a prior transplant, so we wouldn't have to add to their immunosuppression burden in order to evaluate actually the efficacy of the cells themselves. It was more of a proof of concept type thing. And so what the first patient that we published in Cell, what she had undergone was then we just carried on her immunosuppressive regimen for her liver transplant. We just carried that on. And and of course this is our rationale, but there's on the flip side, there's also the argument that if you had used a non-immunosuppressed, a non-prior immunosuppressed patient, then you could actually remove immunosuppression if you wanted to eliminate the cells. And that's definitely one way to do it. But I think our idea was to manage the safety really on the level of production and at the preclinical level in our animal studies. So we were very careful prior to transplanting these patients. We had first of all, our differentiation protocol really is quite robust in the amount of endocrine specified cells that we do get. So at the protocol level itself, I think we tried our best to get very high purity islets. And then on top of that, we had done enough, I think, we had done hundreds of mice studies long-term as well. So we know the cells are not tumorigenic. We were very sure about that. And then also we had developed very sensitive in vitro assays to make sure that each preparation was free of any residual undifferentiated cells. And then finally, of course, our consideration was, as Dr. Deng said, our transplant site really considers the safety aspect, where we wanted to transplant to a site. The site itself is sort of like, it acts like a localized sort of pocket, and that actually kind of locally restricts the graft itself. That's very helpful. It's helpful for monitoring. It's helpful for transplanting. It's also helpful for just making sure the cells stay relatively they're not dispersed, and also the potential for retrievability is there. So these are the ways in which we wanted to. These are the ways in which we tried to ensure the safety, and so that was what we had done at that time.
Just add one comment for this. So in the future, you'll potentially do cell therapy, or in the future organ or tissue transplantation that has 3 different levels. So xenograft or allograft, autologous cell. But for immune, I think the major barrier for cell product is the immune rejection and how to induce immune tolerance. For these 3 different levels, autologous cell much easier than allo and the xenograft.
Right.
So that's the future, the way to go.
Yeah, it's particularly, I think, salient considering, I'm sure you guys follow this, Vertex halted their trial of like the immunoisolating, right? So like the interface is key even when you have a barrier, just because it's not just adaptive immunity, right? It's the fibrosis that can limit it, particularly when we're talking about secreted factor and the signal interface. So it's really key. But I feel like we're kind of bearing the lead here, and I want to bring it back to this really important result to share with the audience. Dr. Liew, why don't we dig in a little bit on the metrics? Like, we're talking about curing patients here, not treating them, curing. And this was what we've always been dreaming about and holding out as the great hope of cell therapy. And diabetes was one of the first targets. So can you talk a little bit and specify, like, what is the degree of, I don't want to call it a cure, right? But this is a really robust treatment, even at these early stages. Can you talk about some of the endpoints that really underscore the improvement for this patient? And maybe, you guys really went deep and tried everything and made sure that you had an optimized protocol. But even so, when you move into a new platform, a new system, in this case human, there may be some unexpected positive or negative. Can you talk about some things, maybe results that came out unexpectedly from those early trials in the humans, and really get specific about, like, how are these patients doing better post treatment?
Yes. So I think that what we were actually surprised to find, first of all, we build upon what's already established in clinical islet transplantation. So a lot of credit goes to the folks who developed the Edmonton Protocol and and subsequent protocols, where we had a lot we could learn from, and I think that's really important. I think what was really surprising with the stem cell approach to clinical islet transplantation was because of course we had thought about how to come up with a treatment strategy, not just a single cellular product, but a treatment strategy that would really result in quite robust, or that could really match islet transplantation. And so I think what was really surprising was that we found that very soon after transplantation, we found quite a significant C-peptide or insulin secretion. And by 75 days post-transplantation, the first patient, the patient had her insulin requirement had slowly tapered down to 0. And she no longer required insulin as quickly as 3 months post-transplantation. And if it was native islets, that wouldn't be too surprising. But for a stem cell derived transplant, that was the first. We hadn't expected it to, I think, maybe happen quite so quickly. But that was the case. I mean, and it does match our preclinical studies in that we know that the stem cell derived islets, they require a little bit of time, a couple months maybe, to engraft and then mature functionally in vivo. But to see that so nicely replicated in humans, that was really a very pleasant surprise. So in terms of some of the metrics, I think we have in our first clinical study, we had transplanted. Our first clinical study is 3 patients, and basically they've all achieved the same thing, which is within 75 days, insulin independence, no longer reliant on insulin therapy for their daily survival. We see a control of A1C, so long-term glycemic control, A1C recovery back to 5% or so. And basically, we also see their insulin secretion from a graft level. We see their insulin secretion levels return to from 0, from undetectable, to return to normal. And so these, yes. And so a functional restoration of their endogenous glycemic control. And most importantly, the patients report stabilized glycemia and the ability to eat anything they want, to climb any mountain they want. I think that's I think the most pleasant surprise, and what really just how quickly it can happen made us we were very encouraged by that.
Yeah, I call this at that time when we published the paper last year. We very cautiously we call the functional cure, or you call potentially cure, because the patient now this month is after treatment for 2 years. I think maybe 5 years. We can say is it's a long-term effect. I remember 2 years ago in September, the doctor called me to Hongkui. Wow, the patient after 75 days become completely insulin independent. So the first patient, she never had ice cream for 11 years. So she's free to eat any sugar food.
Can we get a round of applause for ice cream?
Yeah, she now has free to eat any sugar food. I think the sugar food is she's change her personality, right? If you never eat any sugar, it's very depressed, the personality. But now she's become very happy person, completely different, the personality. And I'm really happy for that.
Yeah, I mean, being in Hong Kong for 2 days now, I've had a lot of sugary sweets, and I'm a very happy person right now. So I agree with that, absolutely. I mean, these are some really incredibly promising results that we're talking about here from this really early stage clinical trial, and congratulations again on these incredible results. But we like to look to the future as well. I'm really excited for the future. Let's think about next steps, and I think scalability is, of course, another big step here. So, Dr. Deng, considering this is a limited patient study initially, what are the steps that are being taken to ensure that the generation and the transplantation of these CiPSC-derived islets can be scaled up, right, to be reproduced more effectively in a larger patient population? So talk about the scalability.
Yeah, the scalable ability. The first thing is how to make a chemical-induced iPS cell. So this year we published a new paper. The time is just as short as 10 days. We published that paper, 15 donors, 100% success rate. And even including the person has 91 years old. So age is not influenced. So the protocol become quite robust now. So in the future, we can not only use fibroblast, a deep blue site, we can use a PBMC and easier to make, the highly efficient to make iPS cell. And then we also try to make a better functional islet cell and reduce the cost for this. And now we are in the process of recruiting many patients for a big clinical trial. This is ongoing. And in the future, also tried for other, not only for type 1, maybe for type 2, because some type 2 patients also need insulin injection. Mm-hmm. So in principle, you can also use injecting functional islet to treat for this disease. So the future, I think, is quite promising. And I think the key is make the cell safer, better functionality, and also the cost for this. And in the future, especially for autologous cell, and we dream is not to use any immunosuppression drug. That will be ideally in the future, because that's the future direction.
Yeah, that's a good segue, because I mean, of course, we think about the future, and it was highlighted, I think, in the presidential plenary this morning, that now that we've reached this stage of proof of principle and we're getting a lot of clinical trials, really exciting time, but we got to look forward to what the challenges moving, in the near future are going to be. And I think that's about scale, access. How many people can we deliver this? So you talk about type 2 diabetes. So yes, the scale and the scope of the treatment. So Dr. Liew, maybe you could talk about this, because at Reprogenix, that's kind of the hat you're wearing. Is the scale up? How do we get this ready for prime time on a massive scale? But at the same time, we're talking about autologous therapy, right? So it's a different paradigm than the off the shelf, more even in cell-based, but like it's a departure, let's say, from the traditional pharmaceutical paradigm. How are you doing that? What are the challenges, and what's the vision in terms of like, not when exactly, but what's it going to take to get us to a point to be treating, curing this group of patients?
Yeah, you're asking the question I ask myself every day. So we have something really promising now. How do we make it accessible? So certainly one of the challenges facing the widespread application of a stem cell derived islet product would be one is the immune barrier, and then the other would be clinical the scalability of it. So previously, what we had done was we like I said, we worked really hard on our protocol, so we have a really good quality islet. But the process of making that islet is really quite artisanal. Like what we want now is to upgrade it into a from what I like to say is from an artisanal method to something that is a bioprocess, like an actual manufacturing bioprocess that is scalable, that is robust, that is efficient, that is stable. So that's something that we're working on, figuring out how to use bioreactors and things to make good quality islets, but still remaining very faithful to the kind of islets that we currently have. So that's one thing. And the other thing that you touched upon is we have an added, very ambitious challenge, which is not only do we want scalable clinical manufacturing of these islets, but we also want them to be able to be adaptable to an autologous approach. So that means that it's not just that I need to have a really good manufacturing platform. I also need it to be adaptable to any donor that comes our way. And that really is, I think, something that CiPSCs, like the chemical reprogramming platform, really kind of shines in this regard. As the person who's working on the downstream stuff, I actually feel that in our, we don't have necessarily head-to-head studies, but I actually, in my day-to-day work, I am able to see and feel and find that we are actually able with the chemical reprogramming platform, we actually have a really high success rate of generating islets from every donor that we whose iPSCs we make. So we are able to make iPSCs from every donor that we get, and all of these cell lines, we could make 10. We could make iPSC colonies. We could have 10. We could have 10 cell lines from each donor, and basically all of them almost are able to differentiate into islets. It's just a matter of maybe how many cells they make. It's maybe a matter of yield, so I think that having a really robust first upstream chemical reprogramming technology, having a really robust way of getting iPSCs, and then a very robust way of then differentiating them. These are all like they're cumulative, like you say, and then you have the technological capacity to even consider an autologous scalable, a scaled autologous manufacturing approach. And I think that we're getting quite a bit of success with that at the moment. Of course, it's still in development, but I would say we are getting quite a lot of success with it, primarily because our technologies, I think, are rather robust, and I think that that's quite important.
I just made one comment. Like in my lab, we use a lot of product from stem cell technology to maintain the pluripotent stem cell. You don't need to make the medium. You just change the medium, just buy the medium and do it. I think chemical reprogram major advantage is you don't need any learn any technology. You don't need any equipment. You just change the medium. That's all you do. So I think in the future, potentially we can use the stem cell technology, such a powerful you just buy the medium and just change the medium, you make iPS. It's so simple and easy to make very simple, and also the chemicals very standardized, easily to standardize, and then you can make a larger scale manufacturing and easier for clinical doctor. You don't need any technology, learn anything, just change the medium. You can make iPS cell.
This is an organic plug for stem cell technologies, but I'm glad you mentioned it because it really was one of the foundational, I think, tenets of stem cell technologies, that a reproducible method, right? And as you said, and Alfonso Arias, who was a guest on the show long ago, he said, if it's not reproducible, it's art. And you alluded to, I wouldn't say your work is art. I mean, it's highly reproducible, but to make it accessible to every scientist. And that was one of the founding principles of stem cell technologies, and why the reagents were so highly valued is that they did what you expected and they did it every time. And I think that's what you're alluding to with the chemically reprogrammed iPS cells, is that they're the same cell every time and they have the same potential across many patients. So I'm glad you highlighted that point.
Yeah, this has been such a fascinating conversation because we're talking about technologies that are, have been many years in the works. Of course, the initial discovery of iPSCs, the initial CiPSC work, and of course, the clinical transplantation. It's been an incredible journey. Before we open it up to you guys for your question and answer, you get the chance to ask the experts some of your burning questions. I wanted to ask each of you just really quickly, what are you the most excited about the future of stem cell biology just in general? We gather every year at ISSCR, we see more and more of these stem cell technologies moving towards the clinic and clinical trials. But especially since, a lot of the folks here in this audience are trainees and junior investigators, younger folks who are being inspired by some of the work you're doing. Tell us what excites you the most about the future of stem cell biologists. So illuminate the future for us if you can.
The future, I think, is we call the cell medicine. Right? Now is the major challenge is age population. So when you so I think we need what is the future medicine? The future medicine is you live longer and a healthy aging. You need to repair the damaged age, injury, or genetic related disease. So it's just like a car. If you buy this car, the car can run. You can operate for 10 years. Now you want to operate for 20, 30 years. You need to replace the damaged parts. So in the future, if you can generate any desired functional cells, and then you can replace this injury, the age, damage the cells. So you can make this a healthy aging. So it's really big demand for this. But when I joined to enter this field, that's 1998, when James Thompson established the first human embryonic stem cells. It's really hyper. Everybody thinking it's a very near future will accomplish this goal. I joined like in 1998 after. So now it's like 27 years past. So I remember this morning, there's a plenary session, the last speaker highlight. So the first wave is come. The second wave is coming.
Yeah.
I think maybe we can deliver the promise for the second wave. So that's my looking for. I think future medicine, major part of one of the cell medicine. Yeah. That's important.
Candice, how about you? As someone who is much nearer to the trainee phase and was born into science when stem cells were already derived, what are you most excited about?
Well, I think that what drove me to really apply to your lab was I think I was really excited about regenerative medicine because what I felt was that we're able to, like, cells are just so cool, you know, like they like when I look at we make islets every day, and then I've been doing this for more than 8 years, and every time the cells decide, okay, I'm gonna be like I'm a bunch of single cells, but tomorrow I'll be an islet. That organization, that self-organization that they have, is, for me, it's just like it's magic basically. And I think that what excites me about where we are at in regenerative medicine is we're really mastering more and more every day the manipulation of cell state and fate in any way or direction that we want. And I think that everything related to that, whether it be using those principles to develop cells, tissues, tools to treat degenerative diseases, or to provide just any cellular applications, or even pushing that, or even reverse engineering that process and trying to understand changes in aging, changes in pathology, just being able to sort of master the manipulation of cell state and fate. To me, everything that we get to do with that is very amazing. And so I guess what I'm most excited about is continuing in that direction to really finally for us all to have mastery of this process in order to solve problems in the world and lead a better life, I think.
Great. So now it's your turn, guys. We'd love for you to come up and share your thoughts or ask any questions of these two amazing researchers who are illuminating the future.
Wonderful work. Thank you. I heard a term this morning, HLA knockout, and I'm just wondering, is that even a thing to create an off-the-shelf version with no immunogenicity?
Yeah, for me, I look at it because my background of training is in immunology. I did my PhD at UCLA, postdoc also with Dalima immunology field. I think people, I think if we can make, like you said, we editing this. But these things, I think, is good for making like CAR T cells. You don't need to stay in vivo for long term, maybe short term, can help you like kill the cancer cell. You know, that's okay. But to make a functional islet, you probably want this cell stay in vivo forever for 20 years. If this cell you make them, you knock out this HLA, this gene, so the cell will be not recognized by immune system. And then if the cells become a cancer cell or be virus infected, and will be like a privileged site for virus for many things. So I don't think that's the ideal solution for as an autologous cell without editing or minimal editing. That's the future. I think the knockout stem cell is a temporary solution. But if you look at the 10 or 20 years later, like looking forward, I think we have better technology than that.
Well, for my part, I noticed, you know, Arun and I cover a lot of these stories. Sonia Schrepfer, major leader in these kind of hypoimmune stem cells. And yeah, I think the applications are myriad. and the unexpected complications thereof, I think, unknown being the emphasis there. But I wonder if it's an economic decision versus a patient decision, and both of those can be intertwined. You have to scale these things in a way where you have that access. But, if you're the CEO of whatever, you can, I think, rationalize the idea of these hyperimmune cells because you're making a product that is sustainable financially, but also can reach a lot of people. But I think what we will find when these clinical trial results come back is that you're going to have to integrate these, kill switches or some kind of safety apparatus just to mitigate the risk of this idea of that's the problem with the cure, right? This is the rest of your life these cells are integrating, unless you're doing CAR T where it's transient. So I think as Dr. Deng said so well, it really depends on the therapy. But what's so exciting is that there's so many arrows in the quiver that I don't want to say it's a great time to be sick, but it's a better time to be struggling with degenerative conditions than ever.
Congratulations on this great achievement. My question regarding the islets that the iPS designated patient specific autologous. In case of type 1, we know that we have autoimmune defect. So there is no, in my opinion, there's no point to make it patient specific. Maybe for type 2, it's very essential because there is no autoimmune defect. It's only insulin resistance issues. So what's the point, or do you think generating patient specific in type 1 comparing to if I have just from healthy control, it makes any difference for patients or not?
Yes. Actually, my PhD work at UCLA is to study autoimmunity for type 1. I published my first paper, Journal of Experimental Medicine. It's study in NOD mice, autoimmunity, how to kill the beta cell. I think they use autologous cell for like you say, the type 2 is fine. For type 1, they have advantage compared with use allo transplantation. Because if you use allo, the cell, you have to solve two problems, alloimmunity and autoimmunity. But for use autologous cell, you only need to solve autoimmunity. You need don't care if you use alloimmunity, you have to avoiding all kinds of immune cells attack. For autoimmunity, is much focused and narrowed. You don't need to do heavily the gene editing. So this you can fine tuning the process. It's relatively easier. And then if you use it right now, use immunosuppressant drug, you use lower dosage, let's talk, this better way. I think it's even at this stage, you compare with the allo, you use a lower immunosuppression drug, definitely has certain advantage. And if you're looking forward for future, I think you will take and also our experience. Although we have many patients ask for this therapy, all of them prefer autologous. Yeah, everybody worry about the immunosuppression thing. That's the major concern for the patient because they can do insulin injection. Now you need to do immunosuppression drug. So in the future, ideally, we don't touch any immunosuppression drug.
Yeah, you're trading one chronic treatment for another, I guess.
Yeah, I think autoimmunity relatively easier compared with allo rejection. Yeah, that's my thing.
Thank you. Exciting podcast to be part of. Thanks for the amazing work you're doing. Have you thought about using chemical reprogramming to do direct reprogramming to beta cells rather than going through the iPS cell route for this application?
Yeah, actually, we did a direct chemical reprogramming for neural cell. So we published a study, cell stem cell, more than 10 years ago. We used a different chemical cocktail, reprogramming mouse fibroblasts to become a neural cell, just by one step. And then we, 2021, we put this chemical cocktail injecting in the brain, and then you can make a in situ astrocyte become neural cell. So direct reprogramming has certain advantage in the future we can do to boost endogenous regeneration power. But for make the beta cell, why we don't use this for direct reprogramming? Because you use the pluripotent stem cell to generating the beta cell, you can really standardize this process, make it better functional, just mimicry in vivo development process to make it really the product, the cells. It's like a development process. It's not like so simple. It's very complicated, sophisticated. Like many labs, even if you want to make a beta cell, it's quite sophisticated. It's not to make things simple. Actually, it's make simple things become more complicated, but very sophisticated, precisely controlled, the best functionality cell for treat patient. So if you're looking for the product, it's not really find a simple solution. You'll find it's really make a safer, high quality, and really truly functional cells. That's why we're looking for use IPS mimicry in vivo developmental process. Really fine tuning. It's not only make a beta cell. Actually, we make this islet cell to have alpha cell, delta cell, beta cell, and is like truly functional islet. So it's not so simple like a direct reprogramming, just make a simply insulin produces. So I hope I answered your question.
So he's saying, you're welcome to do it. He's not going to do it.
Yeah, just to add to that real quickly, I think certainly each of these strategies have their own advantages. And I think with a diabetes treatment with islet cells, you kind of need quite a lot of islets as well. So going through the pluripotent stem cell stage allows you to leverage the expansion capabilities of the pluripotent stem cells. And so therefore, that meets the demand for the amount of islet mass you will actually need to treat a patient. So yeah.
Just make one comment for this. Before I return back to China, actually I worked in industry for 4 years. So what I learned is in industry, you're looking for the product's stability, reproducibility, and functionality, and you can QC the product. If you do direct reprogramming, for example, in vivo, you cannot QC the process. Every person maybe has a different reprogramming efficiency. You have side product. You want to in vitro generating like today. I think the speaker in the plenary also highlighted you really highly functional cell purity QC. That's a real product. Like you buy in the future, you just buy cell phone. It's a really well manufactured things.
Yeah, I mean, Stefan, you are very familiar with QC, so I'm sure you get what he's saying there. But I've always thought that if we went back to the era of direct reprogramming in its heyday and apply the technologies that we have now, namely single cell, we would get a bit of a spread in terms of the phenotype. Whereas, as you were alluding to there, Candice, it's highly reproducible at scale using the physiological differentiation system because that's so reproducible. Nature really does it the same way every time.
Hello, Professor Deng. Thank you for the very amazing work and sharing you have been doing. I have a rather naive question that may already be related with what you have just said. I was wondering, what's your thoughts on using this chemical reprogramming cocktail to potentially reverse aging in vivo? Like, do you have any insights on this matter?
Yeah, I think a chemical approach, reprogramming approach is not only like generating CiPS, chemical induced pluripotent stem cell. You can do partial reprogramming. So in the future, in vivo, you can make cell de-differentiate, go back to fetal-like cell stage, just like a mimicry axolotl, highly regenerated animal species, increase the cell plasticity and increase endogenous regeneration power. And maybe even can use this approach to rejuvenate some cell types in vivo, right? So you can really, because chemical reprogramming is a stepwise approach, you can really fine-tuning well control the process. That can be in the future applied for this. But that's the future potential application.
Yes. Juan Carlos, Altos Labs, Juan Carlos Esposito Belmonte, really working deep on that de-aging thing. Very hot topic. Well, that brings us to the end of our show today. Thanks again to our guests, Dr. Hongkui Deng, Candice Liew, for joining us for this wonderful discussion. And a big shout out to you guys, the audience. There's a lot of you out there. This is so cool. Give yourself a round of applause. You've been so great.